Common multiple choice questions for AP Statistics. The purpose of this video is to go through a bunch of different questions that are reoccurring type of problems that you will encounter on the AP Statistics test. What I've done is I've gone through several different years of the test, compiled them together, and then saw some of the repeated patterns to be able to help you distinguish what are some of the answers that you would choose on the test. Okay, let's begin. You can see these are the different topics we're going to be going over. The first topic we're going to start on the confidence interval. We're going to do p-value conclusions from my confidence interval. So first of all, let's kind of talk about what type of conclusion you can make from a confidence interval. So in a confidence interval, if this is your confidence interval, this one obviously is here. If you're, whatever the HO is, if it's in the interval, that's going to be a fail to reject because there's nothing new. If it's outside the interval, if it's higher than the interval or lower than the interval, that's going to be a reject because I'm showing something new. So that's one way to talk about how I reject or fail to reject. But now let's revert it to p-value. So when p-value, remember, is low, low meaning less than my alpha level, whatever my alpha level, sometimes I use it at 0.05. This one is using alpha at 0.02. So if my p-value is less than, in this case, 0.02, that's going to be a reject, because I'm saying that I have the p-value, remember, is just the percentage of chance, that the percentage of times that this could happen by chance. And so if it happens a very small amount of time, I'm saying, hey, I can reject and I can claim what we are trying to find. But if my p-value is not low, if it's greater than alpha, that's going to be a fail to reject. So we're going to just put these two concepts together. So if it's the p-value is greater than alpha, it's in the HO is in the interval. The value, when I say HO, I mean this value here. This is mu, sometimes it's p, sometimes it's beta, it's the different things. Okay, so let's go through and see why or why not this would be. This one, first of all, let's see if it's going to be reject or fail to reject. Well, my HO is 40,000, and so this is going to be 40,000 is not in the interval, so this is going to be a reject. And it says, the question says, could this information used to conduct a null hypothesis against the alternative hypothesis at this level of significance? So we know it's going to be reject, and so it says that I'm going to yes. So yes, absolutely, I'm going to reject because that's what I got, because the 40,000 is outside the interval, so I know it's not these. So it's either yes because this, and it says yes, it's contained in the interval, and this is says not contained in the interval, 98%, so everything's the same. And then let's look and see. This one says the null hypothesis would be, and this says the null hypothesis would not be. That's the only difference. So we know that we reject when it's not in the interval. Okay. We're making conclusions from p-values, so same sort of thing. So if you go ahead and you want to read through the problem, you're welcome to read through the problem. And so it says the test statistic was 10.13, and it gave me a p-value of here of 0.0175. And it says which of the following is true, okay? So let's go through and see if A is true. At the significance level of 0.05, well, let's see what happens. At 0.05, since I have a p-value of 0.0175, that's less than 0.05, that would be reject. And remember, when I reject HO means I had evidence to do so. I have evidence to conclude HA. And if you read it on, provide convincing evidence that the correct distribution is different. And that's what it's asking, is different, because when I look at my problem, and that's exactly what it's asking for me to do. All right, so if I look at the next one, at the significance level 0.1, the data, it says do not provide. Well, if it provides it at 5%, it's going to provide it at 10%. It's a bigger one, but this says do not, and that's the problem there. Letter C, everything else here, honestly, doesn't really make any sense. The mean number of customers randomly selected, it doesn't really make any sense. And here's a little hint. Look for your longest answers. Most of the time you're going to see that the longest answers, same thing back in this one. You see this? The longest answers typically are one of the correct answers. Not always, but those are kind of the ones that I would, kind of start with and look out for. And then this is saying no valid conclusion can be made because the observed frequency for one cell is less than 5. That is not observed frequency. That would be expected. So that could be 1 if it was the right one, but that's expected, not observed. Remember, observed just can't be blank. And then chi-squared statistic, it tells me the chi-squared statistic is 49 degrees of freedom. No, the chi-squared, remember, to do this, it's going to be k minus 1 is what we have here if it's a goodness of fit. And if it's not a goodness of fit, it would be row minus 1 times column minus 1. But it looks like that's exactly what we have, is just k minus 1, which is categories of minus 1, so it would be 4 minus 1, which is 3. More conclusions from p-value. So you'd like to read that. All right, so now this one tells me I have a p-value that's really small. So I know I'm just going to kind of tell myself that means reject. That means I have evidence for ha. I reject ho. I have evidence for ha. And the first one says the number, which is correct, the number of degrees of freedom for this test is 8 minus 1 is 7. No, because this is a 2 by 2 table. So as I said, like what I was talking about, row minus 1 times column minus 1. So this would be 4 minus 1 times 2 minus 1, which is obviously not 8 minus 1 is 7. That's not correct. The next one, the chi-squared test should not have been used because 2 of the counts are less than 5. Remember, it's not 2 of the counts. That would be 2 of the observe would be less than 1, meaning blank, right? So that's why that's incorrect. The null hypothesis states that the association between category and opinion are used in instant replay, and a small p-value suggests that the null hypothesis should be rejected. So small p-value suggests the null hypothesis should be rejected. That kind of looks good to me, so I read it again, but then it says the null hypothesis states that there is an association between category and opinion. The null hypothesis states that there is no association. So there is no association, so it's opposites. But it was a close one, so it brought my eye. I had to read it. The small p-value suggests that there is evidence. That's good. I like that. Of an association, yes, and this is correct. Because remember, that's my ha. C was saying that this was my ho, and it had it mixed up. Okay, now we're going to just analyze bar graphs. Okay, we're going to go through this one pretty quickly. They're not very difficult, but the main thing I want to make sure you understand about these is that whenever it's relative frequency, remember that's a percentage. And so I only can compare this part of brand X to this part of brand X as far as numbers. Otherwise, they're just percentages, all right? So, because if I had 100 brand X and maybe 10 here and maybe 1,000 here, then obviously, or 10,000 there, obviously, I don't know that, and then I could compare the problems, but it's going to change within. So I can't compare brand to brand as far as how many have more. I only can compare within. So that's the biggest thing to be careful on that. So let's just do this one here and see. So for A, for brand X, there were more green candy pieces than red candy. As soon as you see that, more green than red, I don't even have to look at the graph because remember, excuse me, I apologize. That's within the brand, so we can do that. So we look at brand X, and I see, okay, green is here. And so green's from here to here. So, and then red is here. So this is red. Well, red was obviously greater than green. And this is green is greater than red. So that's kind of ridiculous. For brand Y, there were more red than green. So brand Y, there was more red than green. That's correct. There were more, this one here is what I was talking about. There are more green candy in X than in Z. As soon as I'm comparing two same thing, same number of X and Y, we don't know how much is in X. We don't know how much is in Z. We just know the percentage distribution. So those we know absolutely cannot be. All right, and the same idea. It's the same idea for it's talking about the sum of other ones, and I don't know, which is no percentage. So again, I'm just going to on this one. So this one says which statement must be true. That's the key here, is that some of them could be true, but you have to look at which one must be true. This one says, of all the students who chose activity B, the greatest number of students were in grade 6. Well, I don't know because I just have a percentage of those in 8th, of those in 7th. I don't know how many are in each of the individual ones. So that's the biggest thing on this one. Let's just jump down. The answer is D on this one because are pretty straightforward. All right, choosing your test. So you're going to see the test. These are very common. And so the first thing you're going to do is remember to do the test is, I'm just going to kind of review for you. We're either going to talk about proportion or we're going to talk about means. If I'm talking about proportion, I'm either going to talk about one sample proportion or two sample proportions. Okay? And with one sample portion, I have either a one prop, and a one prop is when when it talks about a p hat and it compares to a p. I have a chi-squared goodness of fit where I have lots of categories, like M&M colors and stuff like that. A two sample would be like I have a two prop where I'm comparing a P1 hat to a P2 hat. I've got two different samples I'm comparing. I've got also a chi-squared independence, and you're going to see a 2x2 table on that. And I've got one population, and I've got two variables that I'm comparing to see if they're independent from each other. Then I have a chi-squared homogeneity. Oh, that should be over here, sorry, under here. We're good. And that's where I have two populations. Really, this should go here. I should put this one under there. There we go. And I've got two populations, and I'm saying, are they the same? When it comes to means, same thing. I have one sample or two sample. When I have one sample, it's just I have a t, I have a mean, and I'm comparing it. I'm comparing my x bar to my mean to the population. With two sample, I have also I have my paired, and those, of course, are paired together, before, after, husband, wife, paired by products, something like that. And that's when I'm comparing, and I have to have the same number in each one. I have to have a two sample t-test, and those don't have to have the same one. I can have 30 in one and 40 in another. And then those are going to compare one sample to another sample. They're going to compare those together. Then I have a linear regression test. A linear regression test is anytime it's a quantitative variable that would make sense to put it in a graph, a line graph. It's the only one that would make sense in a line graph. All right, so let's look at this one. It says proportion. So immediately when I see proportion, I know it has to be somewhere over here. And it says in some elevated blood pressure, so it's giving me, a national health study reported that the proportion, and so that's a P, meaning that's a national study. And then it says the principal of the local high school believes a portion of students with elevated blood pressure is greater. So that sounds like I have a HO is P is equal to 0.15 and a HA P is greater than 0.15. And it says it uses a large sample. It doesn't tell me what I get, but obviously I'm going to get some sort of P hat and I'm going to compare it to that. And so what I've done is, because now we haven't done, we haven't done it says two. We don't have two, obviously. We said homogeneity is a two-way test. Remember homogeneity, which would mean it would need lots more data. Obviously, it's not means, and it's not means. And so we're going to stick with proportion. Okay, so this one looks a factor manner. I'm looking for the test, and so mean. So immediately means is I'm going to say, okay, I know it's not Z, because remember, I should have said Z, remember, is my proportion, and T, remember, is my mean. When we do our Z test, remember it's P hat minus P over square root of PQ over N when we're trying to find our Z score. And T, remember, is X bar minus mu over sigma over square root of N. There's several other different little forms that it has too, but remember, when it's talking about Z, it's proportion, and T is means. So I'm going to just go ahead and cross out anything it can't be. Remember, this is proportion. All the chi-squareds is proportion, so it's not any of that. Then I'm going to go ahead and start looking and see. I have 200 employees from a factory that are sampled here, and each is randomly assigned to two techniques. And so I have 100 employees here and 100 employees here. Oh, so I've got two separate things that I'm doing, so I know it's not this. So now I have to check, is it paired or is it two sample? Well, let's look. Is the sample independent? It says 100 employees, one technique, 100 employees, another technique. There's no connection to these employees in any aspect as far as what I'm measuring. And so therefore, I am going to say it's a two sample. Okay, on the name the test, as soon as I see something like that, immediately I know it's a chi-squared, either a homogeneity test or an independence test. And remember, those also are called sometimes a two-way test. But I can look through here and I can see there's only one that it gave me that it could be. The chi-squared goodness of fit test, remember guys, looks like this. It has one category. If I'm M&M's, blue, red, yellow, and has one list. The two-way table is only the homogeneity and independence. All right, it looks like I missed a p-value conclusion. I'm putting back there. So let's jump back to our p-value conclusion here. And, oh, actually, no, we already did this one. So let's skip that one. All right, for number 36, I'm here. We're going to now still continue to find the test. So department manager, I look greater proportion. So proportion. So immediately as I see proportion, I'm like, no, not this one. Proportion, remember regression line would be means. It has to be, it looks like a line. And then I know it's not this one. So I know it's either a one sample Z or a two sample Z. So now I'm just going to be searching, is it talking about one or two things? Am I comparing a P hat to a P, to a population, or am I comparing one sample to another sample? That's what I'm going to be looking for. Well, when I look here and I see that I am looking for a coupon and an item and the redeem for 10% off the price. Manager has 500 and 10% would here, independent. And so what I'm looking for is indeed, I have 10% off the price. I have 500 customers that mails 10% off the coupon to be independent of the random sample of 500 customers. The number of coupons each type were recorded. Assuming the conditions are met, what test procedure should you use? Okay, so if I were to do this, I would say that I am looking for a random sample of 500 customers. And the number of coupons each type are recorded, assuming the conditions are met. Okay, so I'm trying to find out how much is different is if they're going to be shopping since I have this says I have two separate aspects of 500 customers. The manager mails 500 customers to mail 10% off to an independent random samples. And that's the main thing right here, independent random sample. So I wasn't reading it well, that these actually are two separate sets of 500 customers. So that's where it's going to have me conclude it. Yes, I have two of them. Sorry. Should have read that a little better. Okay, this one to name the test, the first thing I'm going to look at, SIC, I look and I start reading and I start seeing the type of keyboard and I see what it's doing. It's doing a task and multitask and then I look what it's measuring and it says the psychologist recorded the time it took. And so when I'm reading through this, it's definitely going to be, when I'm measuring time, that has to be means, which means, remember, is T. So I'm going to cross off anything that is Z and anything that's proportion. So now the key is it two sample T where I have two independent populations, or do I have them paired together? Well, when you look at it, the women are getting both treatments. Women are getting treatment 1, and then the woman is also getting treatment 2, so they're paired together. And so that's the key, is that's why it's matched pair, is because those receiving the treatment are paired together. Okay, minimum sample size. So this one I see on the test very frequently, and you just need to make sure you remember what the formula is for this. So I'm looking for, this one all is margin of error. So margin of error, and I look here and I see it's looking for means. So if you look up on your formula chart, and then of course in my calculator, the way I've shown you is that you have remember you have X bar plus or minus T star times the margin of error, which is sigma over square root of n. All right, so the margin of error is this part right here. And so it tells me, this is what I'm kind of looking for, T star sigma over square root of n. Okay, so it tells me I want a margin of error no more than $5, and so that means that everything over here has to be greater than 5. I can't have anything greater than 5. So I'm wanting 90% confidence. So to do 90% confidence, I inverse T, area 0.95, because remember my middle 90 has my tail of 95, and the degree of freedom, Oh yeah, and so the degree of freedom, of course, we don't know because it's n minus 1. And so what we're going to end up using is, since we're doing a 90%, we're going to do a inverse norm, since we don't know this, where we area 0.95 and mean 0, standard deviation 1. Okay, and that's going to get us 1.65. Okay. Now, sigma, it tells me that I have, it says the standard deviation is 35 over square root of n. And then if you just do some math, you end up getting, let's see, actually, let me just do it here. Let's multiply, so 165, 35 divided by 5. So let's get my CAS up here. Oh, squared, and I didn't, so of course, and then square it. So square, so it's 133. So you have to, remember, you can't go bigger, you have to go smaller because, remember, with n, if it's bigger, the bigger the number, this is going to make this, it's going to make this smaller, and the smaller the number, it's going to make it bigger. So I need to make sure that that I always round up. And my math, I think I put 1.65. I think it should be 1.64, which is going to change it just a little bit because it actually comes out a little bit below 133. All right, because this is, remember, if you divide this by 10, this is going to be one number, but if I divide it by 100, then because I'm dividing by a larger number, it's making this smaller, and so that's okay. But if I divide it by a smaller number, it makes it bigger, and so I always want to make sure I round up on these, no matter what the decimal is. So I know mine came out a little bit higher when I showed you my calculator, but that's because I used 1.65, and I should have used 1.64. Same thing for this one, except this now is for proportion. So in the margin of error for this one is going to be z star, and it's going to be p hat q hat over n. And remember, if I don't know p hat q hat, it's going to be 0.5. So let's see. So this is 0.02. And it says 95%. 95% is 1.96. I have that memorized. But if you don't, inverse norm, area 0.975, because it's 95% plus the tail, because this is the center 90%. Mean is 0, standard deviation is 1. And then times p hat, let's see what it says. Television estimate percentage here. And so it doesn't give me a p hat q hat, so we are going to have to use 0.5 over n. And so if I put that in, you guys can just put it in NSolve. And if I put it in, it's 0.02 equals 1.96 times 0.5 times 0.5 divided by x. And 2401 is what I got. So again, x equals 2401. And remember, you round up, not down, so that's why I know it's 2,500. Okay, this one here is means, and so we're going to be using the margin of error equals. Now, I'm using z star. Yes, we use t star typically, but because we don't know the n, we're looking for n. So, I mean, really, if I was showing work on a test, I would do this. Not that you have to show work on this t star, this over square root of n, and then as I'm putting it in, I would say, okay, no more than 12 ounces, 0.12, and then, well, I'm going to use z star. And it's 99.6%, so I'm going to have to do that one because I don't have that one by memory. So menu, stats, distributions, inverse norm, and it said 99.6, so I'm going to use 0.998 because you got to use that tail. And I end up getting 2.878, 2.878. And then it tells me standard deviation is 0.3 over square root of n. So if I do 0.3 times 0.278 divided by 0.2. So let's do times 0.3. And this is divided by 0.2, 1, 2, and then squared. And 51.77. Again, we have to round up. And that one was pretty obvious because we rounded up. But always round up on these because remember, it makes this whole thing bigger, and I am bounded that this can be when it says no more. No more. Okay, go ahead and try this one. The same thing. You're going to be putting in 0.06 is no more than, and this is 90% confidence interval. So for 90% confidence interval, let's just show this one just because so we're going to inverse norm. 90% confidence, we have to use 0.95 because I have to grab the tail, and it's 1.644. And then it is going to be, this one did not give me a PQ either, so I have to use 0.5 over n, put that into NSolve, and you will end up getting D. Okay, self-selection issue. You're going to find that there's issues that that I've seen again and again on these tests that it's asked of what's the problem with it, and the problem is that it's not random assignment, that the person in the experiment is allowed to choose the treatment that they want, and that's an issue. So that's exactly what this one is. Let's read it. In a certain school, students can choose, there you go, whether to eat in the school cafeteria or not. A reporter working on the newspaper polled the students to see the reaction to the changes in the menu of the cafeteria. For each student leaving 1 every 30 minutes, it keeps going. Anyway, then it says, which of the following is true? So it says, because each student is leading was randomly selected and could choose the answer or not is random. This is a random sample of student population. An 89% accurate measurement. Okay, so there's a bunch of problems in this. So for one, because each student was leaving the cafeteria was randomly selected and could choose this answer or not, this random sample and the 89 is an accurate measurement. All right, so no, the problem that they can choose to answer or not causes us to have, of course, non-response bias or so that's an issue there. And this reasoning just really doesn't make sense. When you see the word self-selected, honestly, though, gravitate toward that, and that's probably the right answer. Because the students self-select whether to eat in the cafeteria, the sampling method might be biased. Notice this might be. If that says will be or prove, that's going to be too deterministic. So we like words like might. And so when you see things like that, those should point you to maybe that's the correct answer. The next self-selected issue, again, based on you can go ahead and read it if you'd like. Based on the description of the program, which of the statements is probably true? Let's talk about the issues with this. Because over 90% of the participants claim to be cured, the results prove. If you see prove, you know that's not right. This one says the results can be generalized because over claim to be cured. How do you generalize? Remember, with generalization, the only way you can generalize with a random sample is the only way you can generalize. So it has nothing to do with what they're saying. It has to do with how I sampled. So that would be the problem there. Because the participants were volunteers are okay. We can do volunteers. It just talks about what we can make our conclusion. The study is a census. That has nothing. A census just means I sampled everybody. Because they were self-selected, a person's desire to be cured could be, and notice that, that's really good. Could is not deterministic. The self-selected is the issue. I want to get well, so I chose to be part of this program. That could be a problem. Because the participants held the spire 15 minutes, the study is an experiment, and the results can be generalized to the population of all people who have fear of spiders. Okay, the only way you can generalize, again, is a random sample. Okay, histograms. The big thing on histograms I want you to remember is that the left stuff goes into here. So we know that the minimum possibly is, we know it's greater than or equal to 10. We know the maximum is actually less than 60. If 60 were actually in here, another bin would have to occur. So that's the big thing to see for histograms. And so when it's, when you see big things, you see bimodal, you can call this a gap, things like that. But It says, which of the following must be true about the data? So the mean of the data is equal to the mean. Okay, mean, we don't know. We don't know. I have 8 of, I know it's really tempting to say that it's here. That's the median though, right? But we know the median, we don't even know what the median is. We just know it's somewhere in here, somewhere in there. We know that this, we don't know what this median is, 30 or all the way up to 39. We don't know if this median, we don't know where the data lies. So we just know that they're in this sort of set. So we don't really have any aspect of this. The range, we don't know about the range because I said the minimum, same thing. The minimum here is greater than or equal to 10 and the maximum is less than 60. But we don't know where the values are in any of these. So none of these are able. The only thing we can do is talk about the standard deviation. The standard deviation is the spread, and I can see the spread of the data. And I can see that most of the data for data B is in the center, and most of the data for data A is outside. So I can see that this standard deviation is going to be bigger than that standard deviation. The standard deviation is the average distance that they are from the mean. So on this one here, the same idea, minimum price is 250,000. It has to be, must be true. 250,000? No, we know that it's can't be lower than 250,000, but we don't know that. Same thing here, max is, no, we actually know that it's not 2.5 million because if it were, that one would be another bin. The median price is not greater than 750,000. Well, you can find median price. I mean, you can find the bin. The way I would do that is there's 304 homes. And so if I divide 304 divided by 2, you're going to get 152. So my 152nd point, if I were going to do that, if I add these up, add them up, and what that's going to be, 120 plus 138 is 160, or 158. So my 158th point, or between my 39th point, I guess I should say, and my 158th point is in here, and I'm looking for my 152nd point, so I know my median is in there. I just don't know where it is in there. So that's a good one. Mean is between 500 and 750. We really don't know about the mean because it's we're going to have to do averaging as well. But we do know actually about the mean, enough about it because it's skewed this way. We know since the median is here, somewhere in this bin, we know the median's here. We know the mean has to be a little bit to the right because remember the outliers are skewing it. So it may be in this bin, but it may be over here. But it's definitely not in a bin to the left. Upper quartile is greater than 1.5, and so you could do the same thing. You could say 304 divided by 2 is the 152nd point, divided by 2 again is going to be, and then 150 is 76, so which would be the 228th point. What I did is I did 304 divided by 2 is 152 point, and then 152 divided by 2 is 76. 152 plus 76 is 228. So my 228th point, or subtract 76th point from there. And you do that, and it says greater than this point here, which clearly that's not it because you can see I need 76 points, and that's not there. So that can't be it. Okay, transforming data. So for here, it's telling us, an auditor gave me this data, and then it said, oh, there's an error. And the error said that all areas should have been 100 square feet greater. So basically, I took all my data, and I added 100 to them. And so I want to see, how does this change? How does the mean change? How does the minimum change? How does all these change? So I'm just going to go through all of them. Remember, data of position, when things are positions, so that's just going to shift 100, but spread, that's going to stay the same. So position, mean is position, so that's going to go up 100. Minimum goes up 100. Q1, that's going to go up 100. Everything's just going to shift. Median goes up 100. Q3 goes up 100. Maximum goes 100, but standard deviation stays the same. There's no change in spread because all I had the data here, right? And then I literally, if I were to draw it and say, okay, it's here, I would do this. I say, oh, now it actually just moved up 100. So you can see everything's going to move except how spread out the data is. And of course, that one is going to be, and IQR, I guess it doesn't have the IQR here, but IQR is going to be the same. It's Q3 minus Q1, and it's either going to be this one minus this one, or this new one minus the new one. It's not going to have it change, which is the same thing, which I got A for. Standard deviations stay the same. Okay, for this transforming data, this time I have 4 apples, 6 pears, and 1 basket. Now I want standard deviation. So I want 4 apples, 6 pears, and 1 basket. So I'm wanting to do, I'm wanting 4 separate. So essentially, remember, I can't add standard deviation, but I can add variance. And so I'm going to use the variance, which would be 0.2 squared, 0.18 squared, and 1.88 squared. And since I want them separate, I'm literally going to do 0.2 squared plus 0.2 squared plus 0.2 squared plus 0.2 squared plus, and I have 6 pairs, so I'm just going to do it like this. And then 1 of these. Now that's my variance, and so I'm looking for standard deviation, so square root of that is going to indeed get me 1.97 because they are separate. I have not taken them and multiplied them. It'd be different if I said now, let's say they were in ounces, let's say this was just dollars, okay? And I say I'm going to increase the price by 4 times, and now the price of this is $17, $18 or whatever. Then it does, I would multiply the standard deviation. But in this case, because it's all separate, I'm just adding them separate. For this one here, I have a mean of 120, a standard deviation of 15. Random variable has a mean of 100 and standard deviation of 9. And now I'm asking for x minus y. So this one, for my mean, if you recall from our vocab quizzes, the mean of x plus y, you just add, or x minus y, I'm sorry. You take the mean of x and you subtract the mean of y. And this is one of my standard deviation though. For standard deviation, you're going to do the standard deviation of x and square it to get the variance. Standard deviation of y squared. So I have 15 and 9. So it's going to be 15 squared plus 9 squared. And I'm going to end up getting 17.5. Okay, let's practice this one. This one says each sample has transformed by multiplying 3, then adding 10. So standard deviation is going to get multiplied by 3, and mean is going to get multiplied by 3 and added 10. So let's see. It says the original sample had a variance of 4. Okay, so what's the variance of the transformed sample? Well, if it had a variance of 4, that's a standard deviation of 2. And I say, okay, what am I going to be doing? I'm going to say, okay, well, that's going to be 2 times 3, which is 6, but that is my standard deviation, and I have to square that to get back to my variance, which is 36. Okay, transforming data when adding and subtracting from the data set. So this one is telling me which of the following statistics in grams for the field has the same value before and after the adjustment. Well, all that happened in here is the student adjusted by subtracting 3 grams from everything. So this is going to change, 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 because those are measures of position. It's the IQR that doesn't change because that's Q3 minus Q1. So if I had an IQR of 100 minus 97, and now my new IQR, or my new Q3 is 103 minus 100, obviously I'm going to get 3 and 3 at the same time. Okay, now for transforming data. This now is asking you to change this to go from Fahrenheit to Celsius. And so, but I don't want to do it, I want to do it with standard deviation. So basically what's going to happen is this. That's what's going to happen. So that's why you're going to get this one here. Because what happened is, remember, it's shifting. So the shifting just moves the data, and it doesn't cause any of the problems to change. But what I'm doing is I'm just multiplying by my standard deviation of 0.4. Okay, suppose the scores have a mean of 47, standard deviation of 14. I'm adding 4. So 4 should add to that one, and it shouldn't affect the 14 at all. So that's what you're going to do here. It says, so which one is it going to be? So you're going to look for 14. So we know, no, it's not that, it's not that. So it's either this one or this one. And obviously it added 4, so it's this one. Because standard deviation is just the spread, and it just shifts if I'm adding it.